Alright, we're going to go over some of these problems. I'm only going to do the ones that go through the math, since we've talked about these more conceptual ones. If you still have questions about those. The big idea here is the impulse momentum theorem. And I'm just going to copy that to a sketchbook. Command 4. Open up my sketchbook. Paste it there. Whoops. I did the wrong button, sorry. It's Command Control Shift 4, I think, if I want to just paste that. Copy and paste it into my sketchbook. There we go. Alright. And what is this all about? This is all about the idea that, let me get a pencil, I'm going to draw in orange, move this out of the way. The idea that a force times a time is equivalent to a change in mass times velocity. So that essentially we can say that force, which is a vector, times time, which is not really a vector, time goes in one direction, is equivalent to the change of the mass of an object times its velocity. And velocity, again, is a vector. And we can use this to figure out all sorts of things. Usually we will know 3 of these things and then can solve for the 4th thing using some basic algebra. So let's look at the first problem. Okay, the first problem is I'm going to talk about here is number 2. I'm going to paste it into my sketchbook. Okay. Before we do this, I'm going to basically show you both situations in my simulation algorithm. Whoops. So, this program is not great at letting me do both at the same time, but I'm going to show you first the first situation, which is we have a material with a velocity of 1 meter per second, and in this program it doesn't let you really change how elastic something is, but I can make something definitely stick if I make both the ball have a restitution of 0 and give the ball and the wall a restitution of 0. That means it's going to stick. So what is the momentum right now? I'm going to take a little screenshot of that and paste it in my sketchbook. I love, it didn't work. Not hitting the right button. Command Control Shift 4. There's my ball. Sketchbook. Paste. There we go. Alright. So there's before. In all these things we're doing before the collision, during the collision, and after the collision. In this case we only know about before the collision and after the collision. We're not worrying about during the collision. So there's ball A. I'm going to write, first of all, this is before. I need a thicker marker. Do thickness, thickness, thickness. Here, I'm going to use a pen. Oh, that's too thick. Oh, that's too thick. How about a pen? Ink brush. Before the collision. So here's our object A, and it's got a momentum of 1, or its momentum is mass times velocity, this equation, and its mass is 50 grams, which is 0.050 kilograms, because kilograms is per standard unit, and its speed is 1 meter per second, so times 1 meter per second gives us a total momentum of 0.50 times 1, anything times 1, is not going to change at all, so that math is easy. 0.50, and the unit kilogram meters per second. Okay, and now let's see what happens to it. Run the simulation. This comes to the wall. Boom. It should have stuck. It's supposed to have stuck. Simulation didn't work that well. Now its momentum is 0, because mass times, doesn't matter what its mass is, its velocity times 0 is 0. And sorry that didn't stick as well as anticipated, but oh well. Get the idea. Okay, back to my sketchbook. So after what was the momentum is 0.050 times 0 equals 0, and I didn't write the units there, kilogram meters per second. So that means, what was the change? Well, the change of momentum, we write delta P, P is the symbol for momentum, is the initial momentum, the final momentum, minus the initial momentum. And our final momentum was 0 kilogram meters per second, minus our initial momentum, which is 0.050 kilogram meters per second. And 0 minus 0.050 is negative 0.050 kilogram meters per second. Okay, I'm going to save that. Control-Shift-4. So this is for object A. Now I'm going to delete a bunch of this. Can't do with that. Where's my eraser? Panic, panic, panic. Panel selection. That's where I get make my pencil thicker. But I want to select this, delete, delete. So object A, delta P, 0.50, and again that was for object A. Change momentum negative 0.050. Now we have an object B. I'm going to run the simulation on that. Again, what was our object's initial velocity? 1 meter per second. And it's going to be a little bouncy. So I'm going to try to visualize that. Frisson, I'm going to give a restitution of 0.8. I think that will actually work. Give the wall the same restitution. Maybe that will work. So here's before. It goes to the wall, da 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 da, and it bounces. But now it's a little slower. And we can even look under information. Let's move everything. So you can see what I'm looking at when I do this, because I recommend using this program. The information, I gotta put this up here. Momentum, negative 0.04, which is actually exactly what we're gonna get when we do the math. Okay, so this is for the change of particle A. I'm now going to switch colors for particle B to blue. So for the second particle, we have this thing B. It's got initial momentum of P is mass times velocity. Its mass is 0.050 kilograms times its velocity, 1 meter per second. That's our before. And then we have our after. Because again, we're always going to do this before and after, and during if the question gives us information about during. This one doesn't. So after, so this is our P initial. Then we have our momentum final. Well, it's going 0.8 meters per second, but to the left. And when we're talking about vectors, to the right is a positive, to the left is a negative. Now, it didn't say negative meters per second, but it did say away, so we have to use our brains and realize that away, if one's positive, the other's got to be negative. So the momentum here is its mass, unchanged, 0.050 kilograms, times negative 0.8 meters per second. So our final momentum is 0.050, final momentum is this times this, which is negative 0.045 times 40 kilogram meters per second. So our change in momentum for particle B is, again, the final momentum minus the initial momentum, and the final momentum was negative 0.040. I'm going to leave out the units just because I don't have much space. Minus the initial momentum, which was 0. I didn't finish it here. 0.050 kilogram meters per second. So negative 0.40 minus the initial 0.050. And if I have negative 0.04 minus negative 0.05, I'm going to get negative 0.090 kilogram meters per second. So what does that all mean? This time I will try to lasso this properly. Delete all that. Good enough. So for particle B, the change in momentum was negative 0.090 kilogram meters per second. So we look at A, it's negative 0.050. If we look at B, it's negative 0.090. So now getting to the problem, which changed more? Greater change in momentum. Well, this is the absolute value of this is larger than this. This changed by a 0.05. This changed by 0.09. So this changed more. And our math is our reasoning. Okay. Let's look. Okay. Hummer in a VW Beetle, Charlie speeds. Have a head-at collision. This is all conceptual, so I'm just going to talk about it. We could use numbers, we could make up numbers if you want, but I'm going to have just basically we have a big object and we have got a small object. And I'm going to give this an initial velocity, it's negative 1, and this one initial velocity that's also 1. But this is a bigger mass because it's bigger. I want to visualize the momentum. Boom, there's its momentum. It's big. Because it's big, because it's got a lot of mass. Visualize this thing's momentum. Oh, that's not right. I'm going to make this thing's mass, say like 1 kilogram, and this thing's mass, like 100 kilograms. And why are these momentums equal? They should not be. Well, anyway, we'll hit play, see what happens. Okay, again. The momentum of the object on the left changed imperceptibly. I'm going to see if I can get this. I don't want to visualize momentum if it's going to be so silly and not. The arrow should be proportional. Anyway, so, boom. This thing didn't slow down much, so its velocity didn't change much. Momentum didn't change much. This thing clearly looks like it changed its velocity a lot because it's going to the left and then it goes to the right. Boom. But we have some things we need to, some rules we need to think about. So let's copy this and go to our sketchpad. All right. So the big thing here is obviously one of them is more affected, and that's the smaller car. But okay, here we have newtons. Okay, third law. Every action has an equal and opposite reaction. So that means that during this collision, right here, right there, let me go back again. Let me even do it in slow motion. Here they come. The second they hit, the forces must be equal and opposite. So right now, they're both experiencing the same amount of force for the same amount of time. So the forces are equal but opposite. And if they experience the same amount of force over the same amount of time, well, that's the whole impulse momentum theorem. A force, same amount of force, same amount of time, is equivalent to a change in momentum. So, same force, just opposite directions. Due to Newton's third law. Okay, which will experience the greater change in momentum. Well, again, the big car, sorry, I hit a button there, it experienced a certain force. Let's give that a random number. Let's just say it was 100 newtons. Okay, and let's just say that collision lasted 1 second. Again, I'm making numbers up. So that's a force times a time. That's a change in momentum. Its change in momentum was 100 Newton seconds or kilogram meters per second. Now for our small car, the force was negative 100 newtons because it must be equal and opposite, Newton's third law. And it had to collide for the same amount of time, because otherwise that just doesn't make any sense at all. How could you have a collision where one thing is experiencing it for more time than the other? That just doesn't make any sense. So here, our change in momentum is going to be negative 100 kilogram meters per second. So, I mean, 100 and negative 100. When you were asking for change, well, the change is equivalent. They're 100 and negative 100. It's the same absolute value. So the change is same change. Same change in momentum. Because if we're talking about total change, we don't care if it's positive or negative. Now this is unintuitive because clearly the smaller car, you would prefer to be in the big car, and that's because one of them experiences a great acceleration. How do we justify our answer with Newton's second law? That F equals ma. Okay, or rewritten, acceleration is force over mass. So, our big car has a really big mass, so its acceleration is small. It experiences a force divided by a big mass, and if you divide by a big number, you get a small number. Now for our little car, the mass is tiny. It's the same force. I want to draw that even tinier. But that's going to equal a bigger acceleration. Because if you divide by a small number, you get a bigger number. We could use real numbers, but we don't have to. Yeah. It's just that if you have a huge mass, even if these forces, again, this force and this force are equal and opposite, but the masses are different. So the more massive object is going to have less acceleration. You know, we could plug in fake numbers, we'd make up numbers. We could look up the actual masses of these cars and figure this out. And then, but if we divide by a small number, the same number divided by a small number, it's going to be a bigger number for acceleration. So that's the justification. All right, moving on. Why are padded dashboards safer than hard dashboards in automobiles? Okay, all of these, except for part C, are the same idea. Okay, I'm going to bring up video. Slow motion collision of hard things. Okay. Neodymium magnets, they're hard. And some of you have made the mistake of tying these things together. These things are hard, so there's a lot of force, not much time. Even if you put it in slow motion, not much time. And you get a spark because there's so much energy. Alright. Okay, now let's look at slow motion airbag. Airbag. Head hitting air. Airbag. No. I'm hitting something soft. Landing on a pillow. This is silly. This has nothing to do with things, but oh, that's a nice soft landing. All right. So the thing is, when you're in a car, that was surprising. Either way, your head is going to stop, right? It is moving at the same velocity in either case. But regardless of what your head hits, it's going to end up with a velocity of 0 meters per second. All right? Its momentum, its final momentum, will be 0 meters per second times the mass of your head. It doesn't matter what the mass of your head is, that's going to be 0 kilogram meters per second. Okay? But now we're going to get to this impulse momentum problem. Sketchpad. Boom. Oops. We don't want to lasso. It's going to make me do it. Lasso all of you. Delete. Paste. Alright. So, the big thing is, you're going to have a change in momentum. Delta P is some number. Let's just call it 100 kilogram meters per second. I made that up because it doesn't matter. There's case 1, hitting something hard. Hard or hitting something soft. We all agree that hard things and soft things are different. Now, if this change in momentum is the same, I'm going to say, have the change in momentum, I'm going to write it the same size. Now you could either have a big force over a little amount of time, because again, hard collisions, they take place very quickly. Or you could have a lot of time times a small force. Now which would you rather experience, a small force or a big force? This is going to hurt a lot because it happens quickly. This is not going to hurt a lot, and this all comes again from the impulse momentum theorem. That if the change in momentum is the same for 2 collisions, but the time difference is different, then the force is going to be different. Now there is some confusion here. It's like, well, what if about head bouncing? Maybe the padded dashboard is bouncier. That might complicate things, but this is the idea that they're going for. So, like a good proper answer to this would be, if the collision takes more time, there must be less force because of the impulse momentum theorem. Okay, same exact reasons for nylon ropes, which stretch under stress, favored by mountain climbers. If you're falling in a rope is going to catch you. Here, I can animate this, no problem. I'm going to just have a thing here. I'm going to stick it, go to the background. I'm going to have a dude. Here's my dude. And I'm going to put him on a chain. He's on a chain. And now I'm going to turn on gravity. I'm going to zoom out a little bit and hit play. Oh, I'm going to go at full speed. Ow! That hurts. Ow! That hurts. Again, ow! That hurts. But what if instead that chain can move a little bit Again, it stops you right away. A chain's not going to bend much. What if instead we have like a spring? Because basically the nylon rope is going to act like a spring. It's not a perfect analogy, but it's close. Here's one. Here's our guy. He's falling. This really doesn't do a good job. Ah, he died. Put it here. Here. Now I want to drop the ball up. It's really going to be like this. I'm just going to give this ball a lot of mass. 100 kilograms. Alright, now with a nice rope, you're falling. Oh, but we got stretched over all that time. And then you bounce back up. And you bounce. And this is exaggerated, but that takes a lot of time. That's a lot more time than the jerk you would feel hitting the chain. So, again, do you want to feel that force over a long time or over not much time? And let me fast this forward. I mean, eventually, you're going to stop just because of friction. I'm going to add more friction just to make my point. Eventually, you will stop bouncing. This is going to take a long time. There we go. And now we're like in soup. Okay, so now he stopped, but he never experienced that much force because he was bouncing over a long period of time. Okay, the last thing that was kind of tricky was the problem about the car lengths. Here are three. I'm gonna have a ground here, and I'm gonna stick them together with some rope. Whoops. And I would want to freeze all velocities. Freeze velocities. I don't want things going crazy. They just disappeared. Okay, whatever. Okay, here's a box. We have gravity. Here's a box. These are going to be train carts, by the way. And I'm going to connect them together with a string. With a rope. And I'm going to show two ways. Okay, so I'm going to use my tool that lets me add force, and I'm going to make my maximum force pretty small. So normally when a train starts, oh, I need more force than that. It's pulling, and right there, oh, it's got to pull all that mass at once. It's got to pull all that mass at once, all three masses. But if it backs up, then it's here now. It only has to be accelerating itself, the main car, front car. Then it only has to be accelerating the second car, and then it only has to be accelerating the third car. So it gets going. It has to pull one. Then it has then eventually when the lengths go, it pulls the other. So would you rather pull everything at once because that's heavy? That's three carts all at once, or do you want to pull one, get one going, then the other going, then the other going? Again, this is increasing the amount of time it takes to get that momentum up. So it's the same. These are all the same questions. It's just you might have known that about trains. So if the train backs up, then the eventual change in momentum of the train will take more time, thus less force. The change of the momentum of the train will be the same regardless, or the same whether it, accelerates quickly or slowly, because the train will end up going the same speed at the end. And in both cases, the train has the same mass, right? Yeah. So, do you want a big force right away, small time, or do you want a smaller force over a longer time? This is easier. This is harder. And why make life hard? Okay, I'm now going to open worksheet number 2. Worksheet number 2, okay, two objects with identical velocities. Alright, so, I'm going to make up some numbers here, just so the math is easier. I'm going to say, so object A is 3 times the mass of object B. I'm just going to type in here, and I'm going to type in different color so it's clear. Okay, I'm going to say object A has a mass of 1 kilogram. Object B has a mass of 3 kilograms, because it said 3 times as much. Oh, no. B is... A is 3 times. So if object A has... And they're going the... they have the same velocities. So let's make up a number. Let's say 1 meter per second, because multiplying by 1 is easy. So then object A, momentum, is, again, momentum is mass times velocity. And what's its mass? 3 kilograms. Times its velocity, 1 meter per second. So its momentum is 3 kilogram meters per second. Object B's momentum is its mass times its velocity. What's its mass? 1 kilogram times 1 meter per second is 1 kilogram meter per second. So what's the ratio? Ratio is like 1 to 1, 3 to 1. How many times bigger is one object than the other? Mathematically, it's, you just dividing them, but the ratio is, look up ratios, Google ratios. It's 3 to 1. 3 to 1. Or object A has 3 times the momentum of object B. If I wanted to do that, I would just take 3.0 kilogram meters per second divided by 1.0 kilogram meters per second, and now we get 3. That's the ratio. If I had done it the other way, 1 kilogram meters per second divided by 3.0 kilogram meters per second, the ratio would be a third. That's fine too, but it asks the momentum from A to B, so A should go on top. It should be A divided by B, so this would be A divided by B, which is what it asked for. This one here would be, even if they asked for the ratio of B to A, So this is not what they were asking, so no, don't do that. Okay, find the value of the kinetic ratio of kinetic energy to A and B. Okay, so kinetic energy. There's a formula for that. It is 1/2 mass times the velocity of the object squared. I can use superscript squared. So for object A, what does that mean? For A, that's 1.5 is the same as 1/2 times its mass. Type in KE. 1/2 times its mass, and its mass was 3 kilograms, times its velocity of 1 meter per second. Put that in parentheses to make this make more sense, squared. And I'm not going to do that yet. I'm just going to copy and paste for B. What's different about B? Only the mass. So what is this? Well, 1 squared is 1. So in 3, this is going to be 1.5 joules. Joules is just the unit of energy. If you are concerned about that, ask me about dimensional analysis. Is not something we are really going to get into that much. Here is 0.5 times 1 times 1. 1 times 1 is 1. 1 times 1/2 is 1/2. So 0.5 joules. So what's the ratio? Again, we want A divided by B. That is 1.5 divided by 0.5, which is 3. Its ratio equals 3. So the ratio is 3 to 1. Same as in the above problem. Okay, two objects C and D have the same momentum. Object C is half the mass of object D. Find the ratio of the velocity. Okay, again, we're doing the same thing. I'm going to make up an object C and an object D. And let's say they have the same momentum. Let's say that the momentum, okay, we're going to make something up. They both have a momentum of, let's pick not one. What should we say? How about 10 kilogram meters per second? Because using numbers is easier than using abstract symbols, so just makes it more concrete. You can always make up numbers. So if they have the same momentum, object C is half the mass of object D. Alright, so we've got to come up with something that multiplies to 10. So the difference between these is the mass. Well, okay, I'm going to make up a mass. Let's just say that C has a mass of 5 kilograms. Then D would have to have a mass of 10 kilograms because it says that C is half the mass of D. Okay. So then times some velocity, we get our momentum, which is 10 kilogram meters per second. And this times some velocity equals 10 kilogram meters per second. So how fast must C be going? Well, what times 5 times what is 10? Well, 2. So 5 kilograms times 2 meters per second gets us our 10. And for D, 10 kilograms. Well, what times 10 equals 10? 1. 10 kilogram meters per second. So what can we say? It says the ratio of C to D, so that's C divided by D. And what's the velocity? 2 meters per second divided by 1 meter per second. And that is 2. So the ratio is 2 to 1. Okay. Kinetic energy. Okay, well, we know our masses again for C, so again, let me change color. Kinetic energy, again. Mechanical kinetic energy, 1/2, or 0.5, times the mass, times velocity squared. So for object C, that's 0.5 times the mass. What is the mass of C? It was 5 kilograms. Times 2 meters per second squared. Object D, just going to copy and paste this. Oops. And I'm probably going to put in KE, because I know what I'm talking about, kinetic energy. So paste that, format it a little nicer. So object D, what's different about it? Is its mass 5 kilograms? No, its mass is 10 kilograms. And its velocity was 1. Okay, so first thing to do in our orders of operation here, we remember orders of operation, we do PEMDAS, which means we do parentheses, can't spell, sorry. We do parentheses, then exponents, then multiplication, then addition, then subtraction. If you haven't heard PEMDAS, that's just the order in which you do things. Okay, so here in parentheses we have parentheses, but there's nothing to do with them. We have exponents, so we're going to do those first. So this is going to become, copy and paste this down, but I'm going to resolve this. What's 2 squared? That's 4. But I have to square the units, so it's meters squared per second squared. Okay, and then copy it down. Now here, I don't have any more exponents to deal with. I just have to do multiplication. So 0.5 times 5 times 4. Let's bring up a calculator thing. You can also use Google to do this. I'm just going to do it 0.5 times 5 times 2 squared. It's 10. You know, and that makes sense. 5 times 4 is 20, times a half is 10. So C has a kinetic energy of 10 joules. Now why is it joules? Well, 1 joule is a kilogram meter squared per second squared. And if we multiply these units, we'd have a kilogram meter squared per second squared. So that's the same as a joule. But just know that energy is joules. Now for D, I'm not going to do all those steps. I'm just going to find the answer. Just have to get rid of units because calculators don't like units. But it's also in the same units. 1 half times 10 times 1 squared. 5. Kinetic energy equals 5 joules. So what's our ratio? It asks for the ratio of C over D. C was 10 joules, and D was 5 joules. That equals 2. So our ratio is 2 to 1. Same as yeah. So 2 to 1 for both momentum and for energy. Should I do everything right? Yep. Okay. 2 squared is 4. 10. 10 times 1 is 10. 5, yeah, so same thing. Okay, so something if the ratios of kinetic energy and momentum will be the same. That's the good way for that. Okay, this is the big meaty question, which is kind of hard. Well, it's not hard. It's a lot of steps. We have to use a lot of equation. Or there's all those other ones. Okay. Following question refer to the motion of a baseball. We all know what a baseball is. Okay. While being thrown a net force of 132 newtons, that's a force, acts on a baseball, mass of 140 grams for a period of 4.5 times 10 to the negative 2 seconds. What is the magnitude of the change in momentum of the ball? Okay, impulse momentum theorem. I forget how to spell theorem. I got it right. Says that change in momentum is caused by a force times a time. And so here we have a force and a time. Complete all this. So where's our force here? Our force is 132 newtons. And what's the force? 4.5 times 10 to the negative 2. If you're not familiar with exponents, this is the way to just look at it. It's the same as 0.045 seconds. So, it's not much time that a person's throwing a ball. So, anyway, we multiply these two numbers. This is our force. This is our time. A force times a time is a change in momentum. It's 5.94. So 5.94, the change in momentum is 5.94. What is our units? Well, we've got two choices, and they're really the same. Kilogram meters per second is our change in momentum. Okay. Initial speed of the baseball is 1 meter per second. Zero. Well, what will the speed be when it makes the speeder's hand? Well, here we need to just define what is momentum. Momentum, P, is mass times velocity. Now, we know the change in momentum. Change in the momentum, so the momentum is, again, in this case it started at 0, so if the change was 5.94, its momentum, the ball's momentum, is 5.94 kilogram meters per second. Forgetting an apostrophe. Okay, so we know the momentum of the ball. So I'm going to rewrite this equation. We know the momentum is 5.94 kilogram meters per second. And do we know the mass of the ball? Yeah, we do, 140 grams. But we don't write things in grams, we write things in kilograms. 140 grams is the same as 0.140 kilograms. If you don't like converting units, a lot of places can do it. My favorite website is Wolfram Alpha. It can solve things for you. You just type in convert 140 grams to kilograms. It goes do, and it gives you 0.14, or in pounds or whatever. Okay, so yeah, anyway, times some velocity. So we have number times a number times some unknown. So we do algebra. We would divide both sides by 0.154. And let me show you that. over here. So if we know that 5.94 equals 0.140 times some unknown v, that means we divide both sides by 0.140 because you always divide to get rid of factors. But if I do it on one side, I have to do it on the other side or else they're no longer equal. So what I get is v equals 5.94 divided by 0.140, and that's 42.5. So v equals 42.5 meters per second. Okay, when the batter hits the ball, a net force of 1,150 newtons opposite to the direction, that's going to be important, of the ball's initial motion, acts on the ball for 9 times 10 to the negative 3 seconds, so 9 thousandths of a second. What is the final velocity of the ball? Well, what are we given? We're given a force and a time. Force and time. What can we do with that? We can find impulse. We can find the change in momentum. Hurrah! Let's put momentum on again. How embarrassing. Momentum. Okay, so the change in momentum, it will be the force times time. Impulse is the change in momentum equals is the same word as is. Impulse is change in momentum is the force times the time. Now in this case, I'm going to move to my calculator. What is the force? 1,150. But it's the opposite direction. So it's a negative force. It's to the left. If we imagine our baseball going to the right, that's I imagine the thrower throwing to the right, and I say right's positive and left is negative. Times this number, force times the time. And I can either do this, that'll work, or I could do 0.009. Point is got to be 9,000. So the change in momentum is minus 10. So the impulse, the change in momentum is negative 10.35. So what is the momentum of the ball? Well, the final momentum. The momentum is the final. Well, how to best word this? It had an initial momentum, so we had an initial momentum of up here from this problem 5.94. 4 kilogram meters per second. And then it changed by negative 10.35 kilogram meters per second. So that means we take our, because again, impulse is a change in momentum. So we have our initial momentum of 5.94. We're just going to add these numbers together. Plus, what is our change in momentum? Negative 10.35. So that's our change in momentum. So the ball's new momentum is negative 4.4 kilogram meters per second. Now what was the final velocity, assessing velocity. The thing is, we couldn't jump to velocity right away. We had to go to momentum. But I know again that momentum, just like the problem previously, is a mass times the velocity. And do I know the mass of the ball? Yeah, the mass of the ball hasn't changed. The mass of the ball is still, scrolling up, still 140 grams. So the momentum, the final momentum is negative 4.4 kilograms meters per second. The mass is still 0.140 kilograms, and it's some new velocity. And if you really hate solving one things, we can even do that in Wolfram Alpha. I could say solve, and then I just put in this thing. Negative 4.4 equals, 1.140, 0.140 times x, or times v, or some other. Solve that, and I think it's smart enough to figure out what it's trying to do. Yeah, it says v is negative 22 over 7, 220 over 7, approximate form. About negative 31.4, we can round. So v, or you can just use regular algebra. Negative 41 point, how are we rounding? Oh, sorry, negative 31.4 meters per second. And negative, why is it negative? Because I imagine, let me use my algorithm. What I imagine here is there's a ball, and I'm going to give it a speed, velocity, to the right, and here's my bat, and let's slow that down. I know my bat's not moving, but that's okay. Let me slow it down a little bit. I know that's not what it is, but the point is, it's going to the right. That's positive, 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 positive. Here comes the bat. Here comes the bat. Here comes the bat. Wham! Now it's going to the left. Left is negative. Okay. How large is the force that the ball is versus the bat? Okay, every action has an equal and opposite reaction, says Newton's third law. So that means the force on bat, the force of the ball on bat is the same as the force of the bat on the ball. So the batter hits the ball with a net force of 1150. So if the force of the bat on the ball was 1150 newtons, then the force of the ball on the bat was negative 1150 newtons. But wait, we were saying that this was that the bat on the ball was actually negative because it was to the left, so this would be positive. Anyway, as long as you just change the sign, because forces are always equal and opposite. Okay, this is kind of draw a force diagram for the rocket. Force diagram, if you're not sure what that is. I don't want to, hello, didn't mean to open that up. Let me draw a force diagram. It just means I draw Here's my rocket. Actually, I'm going to get a picture of the rocket. Because it's hard drawing a rocket without it looking like something appropriate. Someone would tease me. Alright, and I want to change the size of this thing. There we go. Okay. Alright, so now what am I told about this rocket? I'm told it has a weight of 4.36 times 10 to the 4th, or 10,000 newtons. So I'm going to keep that over here. 4.36. Okay, so there's a force in our object. We basically draw a dot and an arrow down. 4.36 times 10 to the 4th newtons. And that's going to be negative because negative is down. Alright, what else would you know about this rocket? It has an engine that provides an upward force of 1.2 times 10 to the 5th. I'll draw that in a different color. (1.2 times 10 to the 5th newtons. Now in a force diagram, we have to add all the forces up. It's like tug of war. I mean, if you know, this number, the rocket's going to go because this number is bigger than this number. That means this force is beating gravity. So we have to add these two things together. So a net force simply means add all the forces. Add them up. Thankfully, we only have to do up and down. This is a one-dimensional problem. So let me make sure. Just be careful doing this. Again, you can do Wolfram Alpha. If you're doing hopefully you're using a calculator. If not, you can use a caret in Google or on a website. So we have, again, negative 4.36. Why is it negative again? Because it's down. We have to worry about direction. Times 10 to the 4th. And I'm going to put this in parentheses because I don't want to make any mistakes with orders of operation. It's so easy to do. And then I'm going to add to that the upward force, 1.2 times 10 to the 5th. Well, and on this one, I'll do the thing. Again, there's no difference between the caret, that's the symbol, it's called the caret, and showing the exponent. I'm going to add this together, and I just have to do that to give it me a number. So 76,400. So I've done that. So what is this asking? Well, first I'm just going to write down what I know about the rocket before I do anything. I know that the force, the net force on the rocket is 76,400 newtons. Now I also know the mass of the rocket, assuming that this rocket is on Earth. Now if you did this problem where you assume the rocket wasn't on Earth, well then it wouldn't have a weight, but maybe the rocket had a weight on Earth and then maybe it was in space. Anyway, I can figure out the mass of the rocket because what is weight is gravity on Earth, and gravity on Earth is 10, negative 10, times mass. So that means if I want to solve for mass, what I want to do is, mass then is weight divided by gravity. Okay, And in this case, what is the mass of the rocket? We don't know. That's why we did the algebra to get this equation. And the weight of the rocket is 4.36 times 10 to the 4th. And gravity on Earth is 9.8, but we can typically, we're just going to use 10. I'm not going to put units because calculators don't do units well. But it'll be a mass in kilograms. Bam. Is so 4,360. It's 4,360 kilograms. Maybe I need this information, maybe I don't. But I think I do. Oh, and I am going to need it. For how much time must the engine burn during the launch in order to reach the speed? Okay, so the final speed. Oh, I know speed, and I know a mass now. What is speed times mass? That's like velocity times mass. That's momentum. So the momentum of the rocket eventually reaches a speed, or I'm going to say a velocity of in the upwards direction of 860 meters per second. Now for here, we're going to have to assume that the rocket didn't change mass. Now, of course, it did because that's how rockets work, but we don't have enough information to answer that, to do anything with that. So what do we have? We have, again, force times time, that's an impulse, equals a mass times a velocity. Okay, what was my force? Do I know my force? Yeah, that was my net force from the previous problem. Where did I draw that? Right there. Did I write that down? I didn't. That was really silly of me. 76,400. Oh yeah, I do have that. So force 76,400 newtons. Our time, we don't know. That's what we're solving for. Do we know the mass of a rocket? Yeah, we do. And if you maybe this was the first thing you maybe should have written down, is that we've got some force times time equals the mass. Do we know the mass of the rocket? Well, we didn't, but then we figured it out. It's 4,360 kilograms. And that's the mass times the velocity, and the velocity is 860 meters per second. So we want to solve this for time. So that means if we want time by itself, we've got to divide both sides by this force of 76,400. So time equals 4,360 times 860, all divided by 76,400. Oh, I don't want a fraction. In this program, I've got to do / n to get a number, 49 seconds. So the time must be time equals 49 seconds. That's a reasonable amount of time. If you ever watched a rocket launch, like a big rocket, this is a big rocket, almost a minute. Okay. Problem 5. Oh, 5 parts. My gosh. Golf ball that weighs 4.45 newtons. That means we can figure out the mass. Let's do that right away. Okay, weight again is mass times gravity. Gravity on Earth is 10. So if we take the force of the weight of the ball is its mass times gravity. Recall that gravity is 10. That means we divide both sides by 10. 0.045 divided by 10. 0.045, that's our mass. Okay, so I'm going to add this information. The mass of the ball is 0.045 kilograms. Okay, we take what we know and we can find things we don't know. That's what physics is all about. Perfectly elastic, that means it's bouncy. I can show that in algodo. Let's get rid of this. Let's make sure there's got gravity. I'm going to make sure that the floor is perfectly elastic. Restitution of 1. I'm going to make a ball. I'm going to give it a restitution of 1. No air. Bounce. 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 Perfectly elastic. That's what that means. Nothing's perfectly elastic, but again, you know, do what we can. Alright. A motion map. You don't have to do that. It's basically a graph. It's basically just showing that it goes up and down and up and down and up and down. Yeah, so if you really want me to do it, I will do this. We didn't spend a lot of time on motion maps, and I apologize that. I should have just gotten rid of that problem. But I'll do it. So basically, in a motion map, we're just drawing dots in equal times. So here's the ball, and then basically I'm doing kind of time lapse. It's going down, it's going down, it's going down. Each time it goes down a little further. So here's the ground. Then it's here. Then it starts bouncing up and bouncing up and bouncing up. And that's basically what a motion map is. It's like a little time lapse. And eventually it reaches back at the same height. Okay. I don't know why I really want us to do that. You could have just done drawn a graph. Algodo can do that too. I right click on it, say show plot. What do I want to see? I want to see its, not its speed, I want to see its position up and down. That's the Y position. If you didn't know, up and down is Y axis. So bounce, bounce, bounce. That's way more useful than a motion map. Okay. Time required for the ball to reach the floor. Okay, here we need to use the kinematic equations. And we need to solve kinematic equations. You can look them up. Come on. Some images. There's all kinds of ones. So, no, this is a good one. View image. Whoops. Image. All right. We want to find the one that has. Here's the V's are velocities, A is acceleration or gravity, and T is time. We want to know time. So we want to find the one where we know everything except time. Do we know the change in height of the ball? Yeah. Do we know the initial velocity of the ball? Yeah. Do we know? So yeah, we want to use this one. And I'm going to use the solver thing, just in case you're not good at the math. So the equation is the distance is 0.5 0.5 times the acceleration of the ball due to gravity is 10 meters per second squared, and that's times time squared. And do I know the distance it's going to fall? 1 meter. 0.0. And I want to solve this for time. So I can just type it in and type solve, and it'll solve it for time. Interpreting as does 1 equal that? No, I want to solve. Maybe if I make this a t, it'll know what I'm talking about. Understand what I'm talking about. Yeah, 0.44 seconds. 0.44 seconds. Okay, the proper way to do that, go ahead and do this. Go to my sketch pad. Boom, boom. Okay, I write in the information I know. Again, where's my pen? Here's my delta. Delta means change in height. My change in height is 1 meter. The initial velocity of the ball is 0 meters per second because it hasn't been dropped yet. Times time plus 1/2 times the acceleration of the ball, which is negative 10 meters per second squared on Earth, times the time squared. Now, this thing, anything times 0 is 0, so we can X that out. So then we have 1 meter is 1/2 times negative 10 times t squared. And I'm getting rid of units because units make confusing unless we're doing dimensional analysis. So now PEMDAS, I'm going to multiply those two things, so I get 1/2 times negative 10 is negative 5 times t squared. I want to get t by itself, so that means I divide both sides by negative 5. So I get 1 over negative 5 equals t squared. Is that right? Yep. So then to get rid of that, I want to square root both sides. So t equals the square root. Am I about to... I'm not going to take square root of a number, but it's just going to be 1/5. I can just make the number positive because it's symmetric and it's kind of tricky, but in general, just confirm square root 1/5 should be about the same. Yeah, 0.44 seconds. Alright. Yeah. What will the instantaneous moment be before it checks for? Okay, here I gotta go back to my kinematic equations. Okay. And we're going to be using this one. The velocity of the ball will be the initial velocity, which was 0. And actually, we could use a bunch of these, but this one is simple. The velocity is acceleration times time. Do we know the acceleration of the ball? Yeah, it's gravity. It's 10. Do you know how long it took was falling? Yeah, 0.44 seconds. So, the velocity equals the acceleration, which is 10 because we're on Earth, times the time, which we solved for, 0.44 seconds. It's going to be 4.4 meters per second. Why do we find velocity? And we could say this is negative because it's going down. I'm not going to be picky about that. Times what? We want momentum. Momentum is mass times velocity. We're doing the thing on momentum. This is what our whole unit is about. So I knew the mass of the ball, and so I knew we would have to find velocity. So what is the mass of this ball? I remember I figured it out up here because I knew we'd need it. 0.045 kilograms. So the velocity of the ball, 4.4. What's the mass? 0.045. 0.198, all our rest round that to 0.2. Momentum equals 0.2 kilograms per second. Now, instantaneous momentum, that means just like the instant before it hits the floor. Like 0 seconds before it hits the floor, yeah. But not before it hits the floor, but 0 seconds. Instantaneous is kind of a funny concept. What will be the change in the momentum from the instant where the ball collides with the floor until the instant it rebounds from the floor? Okay, so I have to draw this vector diagrams. I mean, any words in here, ask me or look it up. Google's your friend. I don't want to look at this. Go away. Okay, now our signs are going to matter. By signs, I mean positives or negatives. So, let me look at. Oh, family's home. Not quite done yet. Almost done though.
Oh, sorry.
So change of momentum. Okay, remember our momentum was. Daddy's working hard. 0.2. So we have a ball going down. Its momentum is what's called now negative 0.2 kilograms meters per second. Then after, it's going up, and if it's going the exact same speed, it has the same mass. This will just be now a positive 0.2 kilogram meters per second. And what's the change? Change in momentum is P final minus P initial. Or in the final momentum was 0.2 minus, minus a negative 0.2. Two negatives becomes positive, so it's going to be 0.4 kilogram meters per second. Suppose the ball was in contact with the floor for 4 times 10 to the minus 4 seconds. What was the average force in the ball was contact with the floor? Well, okay, impulse. Okay, a force times a time equals a change in momentum. Our change in momentum is this 0.4. Is 0.4 kilogram meters per second. Although, is that really what one is? Was I given force? Was it given time? Or do I want to do this the other way around? Because I also could say that 0.4 kilogram meters per second equals the mass times velocity. Well, I'm given time here, so no, it's going to be the other way around. So, some force times this time, 4.0 times 10 to the negative 4 seconds, equals the change in momentum. Change in momentum is 0.4. Okay, that means I have to divide both sides by 4 times 10 to the minus 4. I'll use mine. So, that's 0.4 divided by 4 times 10 to the negative 4. 1,000. Nice even number. Confident. So the average force would be 1,000 newtons. Done.
That's ridiculous. Those are cheese? Those are funny cheese.